I'm standing here in the Senckenberg Natural History Museum because we just published a study in Curr Biology in which we've been able to make the most detailed reconstruction of a dinosaur so far. Furthermore, because of the color patterns that is preserved in the fossil, we can also say something about the habitat that it lived in. Usually when you get a fossil, it's only the hardest parts that are remaining, such as for example bone or shell. But under exceptional circumstances, you can get soft tissues as well. One way is by the soft tissues being replaced by minerals, like we see in this cephalopod fossil here from the latest Jurassic of Bavaria in Germany. In this case here we have muscle tissue preserved. But in other circumstances you can get original organic molecules retained in the fossil as well. One of the discoveries that we recently made is that the pigment melanin can preserve in fossils. This is the pigment that gives colors to our hair and our skin, as well as to bird feathers. And what it means is that we are now able to reconstruct aspects of original colors and color patterns in fossils. And we have applied this to look at fossils like these exceptional specimens here from a locality nearby called Massel, which is about 49 million years old. But we also looked at feathered dinosaurs and been able to reconstruct original color patterns of these. Whilst some dinosaurs were covered in feathers, others were covered in tough skin, like we traditionally had envisioned all dinosaurs to look like. And we know that because some dinosaurs actually preserve skin impressions, like for example this 70 million year old hadrosaur from North America. But unfortunately the way that this dinosaur got preserved did not allow for the melanin to be retained in these skin impressions. So unfortunately we're not able to infer colors and color patterns from this particular specimen. Now there is an extraordinary locality in northeastern China in the province called Liaoning, where you find dinosaurs preserved with soft tissues. From this locality, we've found feathered dinosaurs of all types of sorts, but we also find some so-called naked dinosaurs, like this specimen here. Now, this specimen is called Psittacosaurus, and it's a Labrador-sized dinosaur. It's a close relative of Triceratops in the group called the Ornithischians. And as you can see, this specimen is absolutely spectacular. The skin remains intact, and as you can see, the skin has got different sort of amount of dark and light material. And if you look more closely at it, you can see that it's in places forming distinct patterns. It's very clear here on the hind limb where you have stripes, you have spots, and you have reticulating patterns. Now we have taken some of this dark material and then analyzed it in a so-called scanning electron microscope. And what we see is that it's composed of tiny little oblate structures called melanosomes. Melanosomes are the little organelles in which the melanin is synthesized and also housed. So that demonstrates that what we have preserved in the animal here is indeed the material that gave color to the animal. But the fact that we see these color patterns also support this, because not only do we have these patterns, but they're also symmetric on either side of the animal. So the patterns that we see here, we can also see in the other hind limb up there. And there are some distinct patterns on the forelimb that we can see on either side as well. Now, one of the more interesting patterns that we see in the animal is that it's got a lighter underside compared to the top surface. We can see that very clearly, for example, here in the lower part of the belly. It's very light, and then when we move up onto the back, it becomes darker and darker. And we can see that also in the tail. Now, this is a pattern called counter shading, and that's the focus of our paper now published in Curr Biology. So as you can see, there's lots of remarkable colors and color patterns in this specimen, and also a lot of details of the scales and the different parts of the body. So we thought this would be a fantastic specimen to make a physical reconstruction of. And this was where the paleoartist Bob Nichols came into the picture.
The reconstruction process started, for me, with a flight over to Frankfurt, where I spent 3 days studying the fossil at the beautiful Senckenberg Museum. And while I was there, I used cross-polarization photography to bring home lots of really detailed photographs of the fossil and lots of measurements too, so I could use that information to make a perfect reconstruction. The reconstruction process for two-dimensional and three-dimensional paleoartwork is the same. I reconstruct my dinosaurs and any prehistoric animal from the inside out, starting with the skeleton. Then I add on the soft tissues, and then finally I'll think about the integument. So with all the information I brought home from the Senckenberg, I produced a skeletal drawing, this one here, and then I produced a second with all the soft tissues put onto that skeleton, and then I printed them off at life size so I could refer to them whilst I was building the sculpture. The sculpture process is a complicated and lengthy job. It starts off with a welded armature, which will give the sculpture strength. Then I bulk out the shape with polystyrene, wrap it in wire mesh, and then onto that I put the clay, and that's where all the detail goes into to make it look like a believable animal. And of course, once I've got all that detail into the sculpture, I have to make a mold, otherwise it will dry out and fall to pieces. So I build a mold using silicone rubber. Then over that I put a rigid jacket of acrylic resin, and then you take the mold apart, which is a complicated process, and make a casting, a perfect copy of the clay model with fiberglass. From the mold comes a casting, which is a perfect copy of the clay model. And then the first thing I do will clean up any gaps, because it never comes out of the mold perfectly. And then I'll insert the glass eye and then start painting. And for this project, the paintwork was really complicated. There was an awful lot of information to put onto the cast, and it took about 3 weeks' work. So here is the final model. And one of the greatest moments in paleo art for me is when you produce an artwork and it surprises you. It doesn't look how you expect it to have been. And that means you followed the fossil evidence rather than any kind of preconceived idea you might have in your head. So let me just run through some of the features that surprised me and really interest me. To start with, it had a much larger, wider head than I expected. It seems for at least this species of Psittacosaurus, a wide head was a sexy head. There are lots of details that I took directly from the fossil, like you can see here in the neck, and these amazing clusters of highly pigmented scales at the shoulder, really small scales on the hand and the foot, larger scales in other areas like the knee or the elbow, and of course these amazing skin flaps at the back of the leg with some fantastic detailed skin patterns. You can see that there's a different pattern here to the inside of the leg, and also highly pigmented cloaca. And then finally, these amazing tail quills. And they're even bent into the shape that you can see in the fossil.
Having constructed this model, we were then able to investigate what these color patterns could tell us about the lifestyle of Psittacosaurus. We therefore turned to behavioral ecologist and expert in camouflage, Professor Ines Cuthill, who was able to explain how countershading functions in nature.
Look at this cylinder. It's a uniform grey, but you know that it's actually curved because of the pattern of shading. Illumination comes from above, and therefore it's lighter on top than it is on the bottom. Over 100 years ago, the American artist and naturalist Abbott Thayer realized that this could perhaps explain why so many animals have the reverse pattern of shading. They're darker on their backs and lighter on their belly. Thayer proposed that the gradient of pigment on the animal cancels the gradient of illumination from above, and therefore makes the animal appear flat. Cues to shape from shading disappear. However, the best counter shading to balance the effect of illumination depends on the sort of light environment you're in. If you're in direct sun, there's a sharp gradient of light to dark from above to below. But if you're in shade, such as in a forest, then the gradient is far less pronounced. So by looking at the patterns of counter shading on an animal, we can predict what sort of environment it lived in. And that's exactly what we did for this dinosaur.
We then placed a uniform grey model in different environments and were able to see where the shadows were cast on the model under these varying light conditions. We then compared the transition in shadows to the color patterns visible in the fossil. Our analysis show that these patterns were best adapted for living in a closed habitat with diffuse lighting, such as a forest. This conclusion, that Psittacosaurus was a forest dweller, fits with other evidence from the same fossil deposits, in which we can also find petrified tree trunks and plant remains. By using such analytical techniques on this sublime fossil, we were able to use color patterns to infer the environment in which a dinosaur lived for the very first time.